idea of like finding solutions to nonlinear system equations that have structured solutions, right? So, if you're talking about linear equations that are, have unstructured solutions, they're kind of in the realm of standard linear algebra. If you have linear equations with structured solutions, you're kind of in the realm of compressive sensing. Sort of ideas for compressive sensing, in particular this lifting idea that was mentioned in the last talk, has been used a lot to study like unstructured solutions to nonlinear equations. And then there's been some specialized techniques that kind of put both together. So what we're kind of after here is sort of a general flexible framework to try to understand what's going on. And so we'll see, we'll sort of combine tools in our analysis, ideas from kind of convex geometry and statistical learning theory in the end. Okay, so before I go on, I have to note that sort of the intellectual driver of this is a person I've had the pleasure of working with the past 2 years. He's a very talented postdoc, Sohail Bahmani, and this is kind of, a lot of this is really sort of his vision. Okay, so here's the general problem. So like I said, it's very basic. So there's some unknown parameter or signal or response x star. We'll just say it's in Rn. And what we see is, I just call these measurements, but it's basically we see m different nonlinear functions applied to x star plus some noise, right? And so, okay, so I mean, and the goal, of course, is to, given these observations, I know these Fm and observe the y, is to stably recover this x star, right? So, whether or not you can do this, what's a good idea for algorithms to try, of course, depend on sort of the nature of these f. There might be many different things we'll consider, but in this talk, our kind of primary model is going to be that these Fm are convex, right? And we'll look at problems like, okay, how many of these equations do I need to recover one of these x star and do so in a stable way? And of course, that's that's going to depend a lot on sort of what the nature is of these Fm, and I'll have a random model for drawing them and kind of what the distributional properties are of that model and how they interact with x star. Of course, will all play a role. Okay, but for now, that's the basic problem. So just a couple, one thing to emphasize. I mean, I don't think it will go unnoticed in a room like this, but just because these functions are convex doesn't mean it's easy to solve this system equation. You think of convex optimization, you immediately think, okay, I have many tractable ways I can solve this thing. But what you sort of try is, okay, let's set up a loss function and minimize it. So typical loss functions you might try, they're not going to be convex even if Fm is convex. Least squares is definitely not convex for general convex M. So just because the F are convex doesn't make it an easy problem. Okay, so just two examples. So one example we'll return to a couple times I'll talk. We're actually, we'll have look at we'll actually motivate a lot of the kind of the geometrical ideas using this one example. Is this idea of phase retrieval. There's been sort of a lot of progress on this problem in the past 5 years in the kind of mathematical signal processing / compressed sensing community. It's also kind of the easiest example you can think of as a nonlinear system of equations like this. So I'm it's kind of I'm quadratic now in my unknown vector x star. So I take a simple linear measurement and I just square it, and maybe I add some noise. All right, so there's lots of applications for this. A lot of these in coherent imaging. I mean, where it comes up in coherent imaging is you have a wave which interacts coherently with the environment, but when the wave comes to the sensor, for whatever reason, you can only measure its intensity. It's also, ideas like this are also sort of used a lot in signal processing, like passive system identification. So if I drive a time-invariant system with noise and listen to the result, I can sort of average out what its autocorrelation function is, and then you can recover the response by doing some kind of phase retrieval. Okay, so it's an important problem by itself, even outside this template of an example of a nonlinear system of equations. Okay, so another example, just a simple two-layer neural net. Say if I fix, one set of the weights, say they're positive, and just let this sigma be some convex nonlinearity. You can think of this AM, these different data points coming in. The mapping that they go to the responses y is then convex, and I can think, okay, if I want to fit these weights x, the response layer in between, training this kind of single layer, if you will, with the weights at the next layer fixed, then again, this mapping is convex, but by no means does this make this a naturally an easy problem. And just another sort of thing where we play around with these ideas for is you can also kind of again, if you have positive weights and convex nonlinearities, you can think of undoing the action of maybe you have the second half of an autoencoder, right? So the idea would be like the network is parameterizing some manifold that's quantifying the structure in your data, and so maybe you have another sample point, you want to find the parameterization or good parameterization on the manifold. You might want to solve for the input that caused this. And again, you can separate this into sort of a series of problems that are like on the last page. Okay, so we're not going to worry anything about these particular applications. It's just to show you there's like particular examples that are kind of driving our study. Okay. So at a very high level, so again, this is so common now. I won't belabor it too much, but a big kind of role is what we're going to do here is we have this kind of hard problem. We're going to show like how to convexify it. There has been on a particular kind of types of nonlinear system of equations. There's been studied almost into the ground recently. This idea of quadratic or bilinear systems. Right, and the whole idea, like was mentioned earlier, is while you can think of if you have a bilinear system where I have maybe two unknown vectors and the observations that I make involve like linear combinations of products of different entries in those vectors, while that's kind of nonlinear in these two observation vectors, it's certainly linear in the cross product of those vectors, so the outer product of those two. So this is again just this idea where you can take like nonlinear equations have a certain structure, this bilinear structure, and you recast them as linear equations on something which is itself has structure, a rank 1 matrix, if you will. So now this makes this idea of solving the system of equations. Now it says, okay, I need to solve a linear system of equations, both a rank constraint, and that's kind of exactly what this field of structured recovery or low rank recovery, compressive sensing, like knows how to do, right? Especially for this convex relaxations for these types of low rank matrices. Right, and so what in this context, one of the main messages of that field is, okay, like systems like this, if I have kind of generic systems of equations that are indeed solvable, that kind of corresponds to like random linear measurements here, and then I can solve those system equations if I have just a few more equations than I have unknowns. Right, so just like a linear system where say the rows are random. Okay, and so. The convexification basically says, once you in this lifted framework, you're looking for a rank 1 matrix that obeys some linear constraints. Well-known proxy for things being low rank is nuclear norm. This is great. It's a convex program, makes it easy to analyze. It's analyzed in the generic case, but it's also been analyzed in cases where these AM are structured and they sort of correspond to things that you might see in certain sensing problems. Okay, so this is one way to kind of, the point of talking about this is one way, that's sort of well understood now to convexify problems that are nonlinear, right? And it works well for, say, second order systems of equations. So system of equations correspond to like second order polynomials. You can imagine also saying, okay, I can play this trick for like higher order polynomials, right? So I can write a third order equation as like some kind of third order tensor that's a cross product of three different vectors, or the same vector if it's like or the same vector if we had copy this idea of it being symmetric positive definite. On fourth order, it might be a fourth order tensor, et cetera. I mean, the problem is like we don't have the same understanding for convex relaxations for tensors as we do for matrices, low rank tensors as we do for low rank matrices. And the other problem is like, here we sort of squared the size of this problem. And if you go to even like third or fourth order polynomials, you're again cubing or raising to the fourth power of the size of the problem. So that obviously becomes quickly intractable. Okay, so then there are other methods for trying to solve those system equations, maybe some kind of alternating minimization. But again, those sort of all revolve around the fact that these things are naturally separable. Okay, so the relaxation we'll look at real quick in a second is we'll say like, okay, we're going to look at ways to convexify this problem that work in the native space. So there's no squaring or cubing of the dimension, yet it still becomes a convex problem. It works with, I'll say, quote-unquote general convex functions. So like convex functions where you have some kind of oracle where you can compute function values and gradients, et cetera. And also because you work in the native space here, what we'll see is we can easily incorporate like regularizers which can enforce or at least encourage some kind of structure in the solution. So, using L1 norm to encourage sparse solutions, or like the nuclear norm to encourage lowering solutions, et cetera. Okay, so the one drawback we'll see, right? So it's a nice sort of convex thing while I'm solving. But we're going to need an initial guess, and that initial guess can be very rough. And then so a big part of the work is quantifying like how rough that guess can be, and you'll still be successful. So it's kind of like a lot of the non-convex optimization techniques to solve problems like this rely on having a good starting point. Here, we kind of rely on having a similar kind of starting point. We can really understand the stability of the solution using convex geometry. Okay, so here is the basic idea, right? And we'll run through the basic idea for this approach. In the case of the quote-unquote phase retrieval, again, all this means is that that should be ym on top. All that means is the measurements you make, they're just squares of a linear vector of x star. Okay, so if I tell you that ym is like the inner product of x with some am squared, right? So and just say that the x star is real value, like what does that mean? Right? It means that either the inner product is the square root of the measurement value or negative the square root of the measurement value, right? So if you look, what that means in Rn, that means okay, if I have this one observation, what does it tell me about x star? It means it lies on like one of these two like parallel hyperplanes in Rn, right? So that's if I just know that measurement, like without saying anything else, that's one thing I know about the vector I'm trying to recover. Okay, so where the convexification? Convexification is actually very easy. All you do is you fill in the space in between those hyperplanes, right? So now you're saying, okay, there's one measurement. What it tells me, just kind of tautologically, at this point, is I'm lying on this slab in Rn. So this kind of fill in the gap in between these two things. And a little bit more than that. Like, okay, if there's sort of no perturbation in the measurement, that it's on the edge of this slab. So it's on the boundary of a slab like this. Okay, that's great. So that's kind of what you know for one measurement. Doesn't really help you much. But the idea is like, if you take two equations, then three equations, four equations, you start to get this intersection of slabs. And then what that does, it gives you this feasibility region, in this case just ends up being a polytope. So in the end, if you just look at what you're doing, is you're just taking these measurements and you're saying, okay, these observations that I have, they're defining this polytope in Rn, and I know that the solution lives on this boundary of polytope. So here's just like a quick view of this in action. Right, so here's just a simple example in R2. Like this blue dot is x star, and in this problem you can't really tell the difference between x star and minus x star, so that red dot is an equal solution. Right, and so here's like one equality constraint. So I observe the magnitude of one linear measurement, and I say, okay, I live on this slab. I observe another one, so that kind of makes the intersection a little smaller. Observe another one, right? These are aligned, so it makes the intersection a little smaller again. Fourth one is a little better, cuts off the top. Fifth one, sort of goes in the other way, pairs down that intersection a little more. Sixth one, etc. Seventh one actually does nothing because it lies, the polytope we have already lies in the slab that we have. Then, eighth one, ninth one, and then finally 10th one, right? So all we just did here is we took 10 magnitude measurements, right? So we have a system of 10 of these types of equations. And all we're saying is, what those equations are telling us is that this blue dot and this red dot, they lie on this polytope, and I don't think it's an accident here that this polytope, it's all chiseled down, it looks like a pencil, right? And so, again, you're on the edge of this polytope, so you're at an extreme point here, right? And the idea is, okay, if I can analyze this the right way, I can say how an extreme point that extreme is. That just means you're easier to find. So what do we mean by like easier to find? All right, so if we know that x star is an extreme point in the polyhedron, like how do you find an extreme point in a polyhedron, or any convex set for that matter, is you maximize a linear function. All right, so here my sort of just my observations, these ym equals fm of x, they give me this convex body. Right, and now all I do is say, okay, I'm going to come up with a linear function. I'm going to maximize it. Of course, every different linear function I come up with might come up with a different point, right? And of course, like if I were to head right in the direction of the solution, x star, then of course, I'll get there pretty much all the time. All right, but the idea is like, because you shear down this convex set into like what looks like a pencil, you don't have to move in exactly that direction. You can move in only approximately that direction, right? In fact, in this case, you can move in a very bad direction and still get back your your point x star, right? So like if this is moving like way off, almost orthogonal to x star, I can move the other way, even almost orthogonal to x star, right? So it's lots of different linear functionals. My point here is that you can maximize and still get the right answer back, and it's exactly because that point's been sheared down through just having this large number of observations. Okay, and so in this case, it's almost every direction works. So like any linear functional whose normal vector is like in between these two lines will get you there. Anyone between these two lines will get you here, which is equivalently good. So you have to sort of get unlucky here to not get the right answer. Okay, so it's like this phenomena that we're kind of interested in looking at. The first thing, what are we going to say? Like the essential result is for this and for the more general problems we'll look at later, is what you really need is you kind of need something which all it has to be is correlated with your solution. So basically the angle between x star and your what's called anchor vector a naught, or your initial guess a naught, this linear functional that you're maximizing. Basically that angle just has to be not 90 degrees. So if there's some way I can lower bound this inner product by a constant, right? It's kind of important this constant doesn't depend on the dimension, like when we make dimensional statements. And of course this constant will affect the number of, say, equations we need to identify a solution and how stable it will be, etc. But the point is you just need something that's positively correlated, like in a definitive way. It doesn't need to be 0.96. It can be 0.1, right, or 0.05, and that will get you there. Okay. So where might such a quote unquote anchor vector come from? So one place you can get it is just from prior knowledge in this case, right? So say you know the solution's positive, right? Like if you're in the positive quadrant, you're already pretty correlated with everything, right? So if you just choose, say, the middle, the vector of all ones, properly normalized, then that will work, right? Meet this criteria as long as the solution isn't too sparse, right? Like if you're way on the edge of this quadrant, maybe that's not going to correlate appropriately, right? Another example, like in this phase retrieval case, you can actually compute it in a good anchor vector in a data-driven manner, right? So you can say, okay, if I kind of look at the sample correlation matrix of these AM, right, weighted by the measurements that I make, so this YM, remember, is like the inner product of AM with x star squared. If I average this out, like if I have an infinity of measurements, this basically goes to a matrix that has, well, basically, whose largest eigenvalue is equal to, our eigenvector is equal to x star. And not only that, there's a very well-defined kind of spectral gap between where that, what that biggest eigenvalue is and where the rest are, right? And so when you sort of form the sample covariance, you can get a good estimate of that eigenvector from a very reasonable number of observations. Okay, so that's just another, again, it's a point we'll return to again, but you can kind of make these guesses data-driven if you will. All right, so you can do numerical experiments. I mean, I guess don't worry too much about what's on there. I guess the main idea is okay, look, if I have, say, a random system of equations, maybe if I have 1.5 to twice as many observations that I have unknowns, that becomes very well conditioned. Here, if I have a system of equations but I only observe magnitudes, for this particular algorithm, maybe we pay a factor of 6 or 7 or 8 instead of 1.5 or 2. It's just a takeaway. Okay, and also it scales. I mean, here it's we solve a problem with 25 million measurements and over 1 million unknowns. You can solve it in less than a minute, et cetera. So it's just the idea that the program itself is scalable. Okay, so obviously, this idea of phase retrieval, we didn't use too much of the idea that we were measuring magnitude squared. All we did was to create those pictures of this polytope, right? But we could just as easily have any kind of convex equations, use the exact same kind of relaxation, where I sort of just consider the sublevel set instead of the level set as the kind of set that one measurement tells me about. And again, you can imagine, so here's just a case using different symmetric positives, different ellipses of different orientations, and you get the exact same kind of effect, right? So, the idea sort of generalized way beyond these slabs is just, if I have a convex equality constraint, I can obviously draw a one-to-one correspondence between that and just the sublevel set that defines. And the idea is I look at the intersection of all these sublevel sets, and then I do the same thing. I maximize a linear functional, right? And so again, like, you know, when this works is just totally dependent, or, you know, what's coming into play here is kind of like the geometry of the solution x star, and of course, like how the functions intersect at that point x star, right? And so we'll really see what's important is like the behavior of the gradients, you know, how they behave at this solution x star. That kind of determines how, you know, singular this point is, and hence like how long it will take us to whittle down like what something singular we can sort of safely recover it from a broad range of different linear functionals. Okay, so that's all this is saying is like, you know, you basically you have like observations, you know, y equals f of x, and I just relax those to f of x less than or equal to y. It defines a convex set. If I have sort of more equations that I have unknowns, then the solution that I have is going to be at an extreme point, nice and conditioned extreme point of that set. Okay, so that's the idea. This is what I just said. So you have, you know, you just take y of m equals fm of x star. You just relax it by putting less than or equal to, right? So this is a textbook convex optimization problem if the fm are convex. You know, and if there's noise, right? So like well, sort of all the theory and pictures I'll show you are for kind of a noise-free version. But you can always add some slack if there's noise. And you know, everything we'll say today is there's going to be sort of stability versions of all the different results. But you know, the idea is, okay, instead of m constraints, maybe I can just, you know, we'll actually even do to analyze the problem is we'll sort of add all those constraints together, right? Of course, if there's no noise, I can just make this epsilon equal to 0, and that's exactly the same as saying, okay, each of these fm has to be less than or equal to the ym. Otherwise, one of these things lights up and it has to be positive. So you're going to violate this constraint if epsilon equals 0. So these are the same if epsilon equals 0. Okay, so that's that's the kind of this program yourself. So again, like, you know, if the FM are convex, both of these are again textbook problems. Okay, let me also say just very quickly, like, you know, the question is always like, how do you get this initial guess? And there's kind of a trick you can use, right? So the trick that, you know, of course it's all sort of application dependent. What will work depends on the problem, but for different problems you look at, there's maybe one common thing that comes out in areas you know how to do that. And this is the idea of like, you know, if you have a loss function, oftentimes like information, a loss function could be lots of things, but the information about the solution x star, it's kind of encoded in the derivatives. Right, and so let me just, rather than going through this, let me just look at an example of why it's true. So like, you know, if you have, say, a linear problem, so say the f are linear in this x star, right, and so you have like, you know, y equals ax, right, so if I look at the gradient of that at x equals 0, right, what do I really get? I really get like a transpose a x star is the, you know, what that gradient evaluates to, right, and so, you know, if those A are random, that A transpose A kind of gets close to the identity as I get enough measurements. So in the end, you're kind of pointing, that gradient is pointing directly towards the answer. So you can think of taking an anchor vector in that way. And actually, the thing we did for phase retrieval was a little different. So, you know, look at the phase retrieval problem. I look at the first derivative at the origin. It's actually equal to 0. But what you can do is you can look at the Hessian matrix of, say, the least squares loss. And, you know, another way to interpret what's going on there is like, you know, this Hessian matrix, we know that the x star is going to be the largest eigenvector corresponding to that. So again, we form a sample covariance, and then, you know, just use standard arguments about, you know, how close the largest eigenvector is from the sample covariance to the true covariance. Okay, so this is all just to say there's kind of data-driven techniques for doing this anchor construction. Okay, so what does the geometry look like? Now, if I really want to talk about, okay, like, you know, what is the geometry of this system of equations around this point? Like, when is, you know, why is like just maximizing this linear functional that's roughly quarter with my solution? You know, why is that enough? You can actually start from just kind of very basic convex optimization theory and get a good start to understanding like what you're after, right? So, you know, if I have, say, so here's this picture x star. So here I have two sort of ellipsoidal equations. like here's the intersection of their convex level set. So this would be the set I'm kind of trying to optimize over, maximize a linear function over. Right, and you can say, okay, look, if I really do observe like ym equals fm of x star, like with equality, right, then really the optimality condition for this program up here to recover x star, right, that really is just the same as saying, like, look, this anchor vector that I have, this needs to be in the cone of the gradients of these functions that I'm seeing evaluated at x star, right? So here's just a picture of that, right? So if I want to, you know, if I maximize a linear functional, right, of that basically the normal vector to that linear functional, that has to be like inside, in this case, these two gradient vectors. Okay, so in general, like, what does this say? So like, you know, as you add sort of more equations here, right, this cone should get bigger, so that this should be easier to find the solution. Of course, this is assuming that this x star is feasible to begin with. And then, you know, just more generally, like, what's this going to tell us? It's like anything we kind of say about this problem, it's going to depend intimately on kind of what the behavior of the gradients of fm, again, is at the solution x star. Okay, so that's easy. Again, if you want to say make some uniform statement about, okay, this is going to work for all vectors simultaneously that are correlated with x, you know, all you need to say is, okay, the cone of all vectors that are correlated with x star, that needs to be subtended in this, you know, this cone generated by the gradients at x star, right? So that's just, you can do anchor uniformity. That's a small point. Okay, good. Okay, so like, what can we do to analyze this problem? Okay, so one way we'll look at this, we'll say, okay, you know, this at some point, like, this is a nice condition, and it's pretty much like all you can say, you know, unless you have some kind of model about what's going on. So the question is like, okay, let me say I have an A naught that's correlated with x star. You know, when can I sort of guarantee that this happens? And so here's the kind of the analysis we'll use, right? And so you can agree with this model or not, but it's what we have the results for. So what I'll have to say is like, okay, we're going to draw, you know, convex functions just randomly. So there's some law I have, maybe there's some class of convex functions I have that I sample according to some law. That, you know, that's sort of you know, what that law is only going to show up in a second-hand way in the theoretical results we present. And again, it's only going to show up, again, you can think of it not so much as a model on the convex functions themselves, but on their gradients at the solution, right? And so that's really what's going to be important, right? And then the main question that we'll ask is, okay, like, how many equations, you know, given that I have fm with some law, like, how many equations do we need for this x star to be recoverable? Okay, so what's nice about this general question, so again, we don't have any structure here, but what we can say is, like, you know, what the key point is going to be is how these gradients are quote-unquote conditioned at the solution, right? So do they point in just one direction, or do they give us a variety of directions, right? And that kind of means, is this cone going to be big enough so I can fit a lot of different, like, anchor vectors A naught inside there, right? So that's the essential point. Okay, so I guess, like, just the basics of the analysis, and like, here's kind of where we're going to I'm just doing this so we can tie it a little bit to, like, quantities that come up in learning theory, ideas that come up in learning theory. So so again, you know, you can just ask the question. So this is like sort of my penalty for, you know, if these fm are less than or equal to y, am I inside this set or not? Right, and so I can ask, like, okay, when is x star just the solution to this optimization program? And it's, I mean, it's the same answer as for any convex optimization program. It's true if for, like, you know, every point that increases the functional, so maximizing this linear function, any point that makes this bigger, it leaves the constraint set, right? So this Rm becomes positive for any way I take off from x that's that will give me a higher linear function, right? All that means is x is a supporting hyperplane, just like we had before. It's just a rewriting of that statement. Okay, so just quickly, I mean, this manipulation, don't worry too much. I mean, I guess I think the point here is, like, you know, where we again use the convexity of f is we can say, okay, look, let's see what happens if I add some h to this x star. And what I can say is, okay, I can lower bound that by some sum of the positive parts of inner products of the gradient with f with h. So that's kind of like where convexity makes these gradients come out. And then the idea here is not so much this form that you have. I mean, kind of think of the positive part as like, I have this cone that I'm trying to fall in. But really, what the attack here is you have kind of a, you want to show that this is bigger than 0 for every h in some set, right? And so that's kind of like getting a uniform bound over some like random process if these random gradients are also random, are generated at random, right? And so kind of the strategy that you have is like, okay, if I want to show that this is bigger than 0 for all h in some, again, this is just the ascent cone of the program I'm trying to solve. Like what you say is, okay, look, the mean of this sum is sufficiently positive, right? Just call that tau. And then the deviation of the mean from this sum is sufficiently small, right? And both of these hold, in the right way uniformly over this whole set, right? So doing something like this, I mean, this is very distribution dependent. Showing things like this is exactly where this connection into learning theory. I mean, this is you're basically have you're trying to bound the supremum of a set of functions over a set of random points. But those those random vectors are just gradients that correspond to the gradients at the solution x star that correspond to the functions that I'm looking at. Okay, so that's the basic idea. So the kind of key quantity that comes out. Oops, I somehow missed this here. Let me just see. All right, sorry. So I can ask now when this works. And so what you kind of see in the end is, okay, in general, what do I need? Basically, I need a number of equations that scales with n, right? So just like in the linear case. But what I'm multiplying here by is kind of what's the conditioning of these equations. So this is sort of like a condition number for this equation. So what do you mean for the condition number of the gradients? It's like, okay, if I look at like the outer product, so again, this f is just, they're just IID drawn at random for some set. If I look at kind of like the covariance matrix of these f, so it's kind of like the supremum of f, the inner producted with this thing, and I look at like this tau, which is again this infimum over the positive part of the inner product with f and x. If I look at this quantity, this is almost like the condition number of the sample covariance, right? So it's saying like, if I'm kind of isotropic, or roughly, if the distribution makes the gradients even roughly isotropic, then like I only need a little more than n equations. So I can get with a constant number of equations and constant number of equations, times the unknowns. Okay, so that's nice. So sort of like linear, these sorts of systems to solve are as easy to solve as linear systems of equations. Right, and so that's what we said. So it's like, the gradients are approximately isotropic. You can take m kind of like n. Okay, so next thing is we can look at the exact same problem, but we can look at structured solutions now. So like maybe, again, we look at the same system equations. These Fm are known, and we convex, and now this x star is structured, right? And so now, sort of the natural thing to do is say, okay, what I'm going to do is maximize the same type of linear functional, but I'm going to subtract, because we're maximizing, some convex regularizer for the set. And again, the idea is that this convex regularizer, it's attuned to the structure of the vectors you're looking for. So if like, you expect the vector to be sparse, maybe use the L1 norm. If you expect the vector to be low rank, or be able to be sorted into a matrix which is low rank, maybe use a nuclear norm, etc. Right? So it's sort of the exact same approach. We just tack on a convex regularizer. It's just like when you have a linear set of equations with a structured solution, you just take the least squares loss and you tack on a convex regularizer, and then you can say all kinds of things about how the descent cone of that regularizer interacts with the null space of the linear system you're looking at. Okay, so that's again just the basic conversation, and then the geometry. Like, how does this change the geometry? Right. So now you can say, okay, look, I have this sort of same idea as before. I'll say this is this simple example where I had to have just two equations. Right, and then here's I can then, without the structure, what I was saying is I have to be in the cone kind of generated by these gradients at this point. when I add in this regularizer, how does this picture change? Well, again, you can say like, okay, if I do indeed like observe these equations, with equality, I can say that x is optimal. This is just again just KKT. You can just say x star is optimal if and only if like a is in the cone of these gradient vectors plus something in the subdifferential of x star, right? So of course the subdifferential of the regularized of omega is going to come into play here, right? So what's kind of cool there, it's a simple realization is like, okay, adding this structure makes the problem easier in the sense that this set, right, is necessarily bigger than just the cone generated by the gradients, right? So adding in these structural constraints, of course, like sharpens. You can think of it as sharpening the point at x star, which of course like broadens this cone that we can be in. So like this fact that, say, I'm just using the L1 ball here to regularize means I can widen the cone and makes it easier to lie in there. So what does that mean? It means that maybe I can get away with fewer equations to make A naught fall inside that cone if it's going to be larger in the end. Okay, so it's you can ask the exact same question. So like, you start the analysis the same way. When is the solution to this problem? And the only reason I'm writing this down, the only thing that's different is, okay, I can say that this is the solution to the problem when this sort of like, you can call it like empirical hinge loss risk or whatever you want to call it. This function, again, is positive for every ascent vector for this optimization problem. So the point is, this just gives me a different set. Right? So this set is smaller than the set I looked at in the unstructured case. And the idea is, you do the analysis in the same way, and the key quantities that come up are the same as before. And so what you get is like, instead of like these last two, so geometrical quantities, like what you have instead of like the condition number of the of the gradients, I'll call the condition number of the gradients of the point, condition number of the sample covariance of the gradients of the solution. It's like it's the condition number when you're restricted to the set A. So it's almost like a restricted isometry at for the sample covariance of these gradients that you have. And then of course it's like, how do you measure kind of the complexity of this set A, right? You use, and this what very naturally comes out is something which is almost exactly like the Radmacher complexity. So it's kind of a key like standard measure of like how many equations it could take me to do something in statistical learning. Right, so this is these three things. Like these are like, okay, how well conditioned are my gradients? How well do they match with my solution x star? And this is like, what's the complexity of the statistical complexity of the set that I'm looking at? So what you can say is, you can get results like, okay, M basically in the unstructured case just kind of look like this condition number times n. I can remove the n and put this statistical complexity there instead. I can make it stable. So the point is this, the error of the solution is just bounded by sort of something like the signal to noise ratio here in the measurements. And at the end, it's like, if you have sort of reasonably isotropic measurements, what you can say if you're interested in sparse regression. So if these guys, FM, let's just say, then these x stars S sparse, then if you have something which looks like S squared log n measurements, you get back the answer, right? So that's like S log n is like what we're used to for linear system equations. Here we have, again, nonlinear systems, and you recover almost, what you think of as the compressed sensing result, if you will. Okay. Good. So that's, it's nice. You can add, again, structural penalties and get the kind of expected behavior you're looking for. I will say, right, okay, then this is just, so here's just I'll tell you what all these ugly lines mean. So, what this is just illustrating is, okay, like when does this idea of like sparse recovery for nonlinear equations work? So again, just look at like the phase retrieval problem, looking for a sparse vector, which obeys these quadratic measurements. We kind of saw before that like phase retrieval, when things were unstructured, it took us like a factor of 7 or 8. We know from just compressed sensing literature, like recovering a sparse vector from random measurements requires like, empirically a factor of like 3 or 4 times the number of measurements as the sparsity. Right, so here what we get is like we see this starts to work, like where this green line means work, starts to work at like 28 times the sparsity about, and that's, I don't know, something like 7 or 8 times something like 3 or 4 is about 28. So it's kind of combining those two results together and you get this expected behavior. Okay. Good. So I will mention too that there's always this underlying question of how you get this anchor vector. And so for a lot of the nonlinear problems, we talked about this idea of having like a spike derivative and like the empirical loss, encoding some information about the solution or enough that you can get at it and get a decent guess. That's it's also true for structured system of equations. But the problem is like the optimization problems you might have to solve to figure out what that say biggest eigenvectors. That could be like those problems could be hard themselves, right? So you can think of in this sort of general recovering like a sparse vector from quadratic measurements. So in the standard case, we had to find an eigenvector. In the sparse case, maybe you have to find like an eigenvector which meets some sparsity constraint, or like not eigenvector, but like you have to maximize some quadratic form which meets some sparsity constraint, and then you're in this land of like sparse PCA, so it's a hard problem. So the idea is like, look, it's sometimes like constructing the anchor is harder than actually like cleaning it up and getting the solution. So the point is just that either the anchor construction or the geometry, like the geometry we looked at on the previous slides, could dominate like the number of measurements that you need. Okay. So there are interesting cases where we can do it. So let me just end by talking about one such interesting case. So this is, I don't know, it's a problem of some scientific interest, but it's sort of like a special fourth order problem. So the idea is we combine these two problems we talked about already. So you have some like low rank matrix you want to recover, but I don't get to take linear measurements of it. Say I take quadratic measurements of it, right? So again, this is just sort of a template problem. It's a template problem which happens to have some applications, so some channel equalization, optical communications. You can't measure phase. Things get blindly deconvolved with each other. You can think of this as a template for like combining two quadratic problems. So I have two, I say blind deconvolution, but you think of having like two functions that I multiply by one another, and then I only observe their magnitude. Or I take two different functions, I take linear measurements of them, multiply those together, and I only get to observe the magnitude. So again, if you multiply this out, it's some fourth order problem, right? So you can look at this again just as an example of the things. You can actually, use for these phaseless measurements, you can use our relaxation we just talked about. We use kind of this level set relaxation. And for the fact that, say, if you want to recover, say, a rank 1 vector x here, right, you can just say use nuclear norm penalty. So to take care of one, like half of the fourth order, you use this level set relaxation. To take care of the other half, you use like a standard lifting scheme, right? And so if you do this, right, which you could show, and then so you have this program where again this is sort of enforcing these level set constraints, and this is like encouraging the x to be low rank. And so you can show that, like, first of all, you can develop an anchor vector for this just by looking at eigenvectors of different empirical covariance matrices, right? And then you actually do the analysis that say, okay, like solving this convex program, and then getting some solution x hat, and then factoring it to get the low rank factors. You can say that, okay, look, if I have sort of a number of measurements that's on the order of the length of these two signals, right, I get stable recovery, right? So if m is within a log factor of d1 plus d2, the angles of these two things, they'll collapse to 1/2. Okay, so that's just like another example of like a sort of problem of nonlinear problem of interest where you kind of have the whole story. You can construct the anchor vector easily. You can turn it into a convex program, and you can get like what's a close to optimal result. Okay, so so I guess what this means is like phaseless rank 1 recovery is almost as easy as linear rank 1 recovery. Okay, good. So that's where I'll stop. We have several papers online that kind of fill in all the gaps, like I'm sure you're wondering about, that I left undone here. And of course, I'm happy to take any questions that you have. Yeah.
Very nice talk. So, in this setup that you described, where your new complex relaxation, given enough redundancy, allows you to identify a solution, can I think also like as a baseline to just do naive gradient descent on the non-convex problem?
Yeah.
And does it make sense to compare both runtime
Right.
and also recovery guarantees?
Certainly, certainly. Yeah, so I can tell you what they are. And it's kind of the opposite of what I was expecting when I actually did something like that. Right, so there are nice, say, for the phase retrieval problem, there are nice non-convex optimization things. They work with slightly fewer measurements, so they're slightly more efficient. But actually, like, just using off-the-shelf LP software, this is actually slightly faster in terms of the number of things you have to do. So I don't do with that what you will. But I will say, the proofs here are about the 1/10 of the length of the non-convex optimization. It really is. Like you saw, it really is just convex geometry, and it's just a couple steps away from basic stuff. So in that way, it's like gives you a clean explanation of what's going on.
Any other questions? You said that you can use like any arbitrary convex measurements, right? But
Right.
in some of your proofs you use gradients, so assuming that it's differentiable.
Yeah, that's right. So like everything, so it could be you could make it to non-differentiable things, but like yeah, everything we talked about here, we explicitly use the conditioning of the gradients. I don't know how I would phrase it, but it could be if there's non-differentiable F, there could be a more intelligent way to talk about, you know, what some of the subgradients are in some. I can find subgradients that are well conditioned or something like that, but yeah, I don't know.
Any other questions? So if not, then let's thank Justin again.